to lesson number 10. Before we begin, I want to thank everyone who's been watching the videos and making comments, and those who have also identified some questions for me or some issues that you wanted me to address. Thank you very much. Keep doing what you're doing. I hope you keep finding these videos useful. All right, and now let's begin with lesson number 10, and this is the implied domain for logarithmic and in fact exponential functions. This now hangs on the areas of the higher level mathematics program, but everyone else needs to understand why when we give logarithmic functions, we usually, when we get to the argument, we normally put the modular sign to indicate that it is always positive. Well, we need to understand why this is the case. Okay, so let's get on to this straight away. So before we go to logarithmic functions, I want to talk about exponential functions. So a function is said to be exponential if, so when we write y is a power x, this is referred to as an exponential function because the variable x, the input, is an exponent, right? The value of a can be any positive number greater than 1. So a is any number that is greater than 1, right? So this is what we mean by an exponential function. The x is the input, and when we take a power x, we will get a y, which we'll refer to as the output. So I'm going to write this as a power an input x is always equal to some output y, like that. So let's look at this on that with that understanding in mind. Okay, so this is an exponential function. We want to see what happens to the output of an exponential function. All right. So what happens to the output? So here is a general exponential function. Here we have 2. We are using a as 2 here. So 2 to the power of x, so that's our input there, must give us a value of y, which is the output. Okay. So we want to see what happens for different values of the input. Okay. So the question is, what output values do we get for each of the following input values? All right, let's start with negative 10. So if we substitute negative 10 here, 2 power negative 10 is 1 over 2 power 10. 2 power 10 is 1024, 1 kilobyte, for example. So 2 power negative 10 is equivalent to 1 over 2 power 10. 2 power 10 is 1024, which is the so-called kilo, right, in electronics or data processing. And this gives us approximately that much. That's approximate, that's not the exact value. It's 0.0097 something, but we'll take 98 because we are not keen on the exact value. All right, so if we put negative 10, if the input is negative 10, we get that value. All right, if we put negative 100, we still get a value smaller than this, right? But it's going to be positive. All right, what happens if we put negative 3? We get 1 over 8, which should be 0.125. If we substitute negative 1, we get a half, right, which is 0.5. If we substitute 0, we get 1. If you've studied exponential functions or exponential equations or expressions, if we substitute 1, we get a 2. If we substitute a 2, we get a 4. And if we substitute a 5, we should get 32, right? What you notice is that no matter the value of the input, positive or negative, the output is always positive. Okay? We note that all output values are positive for whatever a real number input. Okay? And this is the important point here. I will try to sketch this. So the range, we are saying that the range are numbers that are positive. If I went on changing the value of x to even smaller negative numbers, negative 100, negative 1000, doesn't matter. The value we get, the output is always going to be positive. So when we sketch the graph of this, it looks something like that. So this is the exponential function. So in particular, y equals to 2 power x would look something like that. The x-axis there appears to be the asymptote. Okay? So we know that for exponential functions, the range is always positive values. All right, so let's move with that in mind. So for exponential function, we can immediately say that the domain is all real values. I can write that down. So we can say that the domain for an exponential function is x values, all real. That's it. All right. There is no other option. And the range for an exponential function, the range is y are all real values such that y is greater than 0. Okay? Y is greater than 0, like that, to infinity, and we close our bracket like that. So that's the domain and range for an exponential function, but most of us will usually know about this. The issue is the logarithmic function. Okay, some of you have gone into the inverse of a function and will probably understand this straight away. But for those who have not, let's try something else. Let's see if we can understand it from a different perspective. Right. So keep this in mind. I'm also going to, in place of input, I'm going to put R to indicate that all real values are allowed for the input, according to what we've just said there. So we start by putting 2 power any real number. We've agreed that 2 power any real number is always going to be positive. If we take the logarithm of both sides of this relationship, okay, we will find that log to base 2, and we are taking log to base 2 because this is the base 2 there. We want to get rid of that base, so we take log to the base 2. All right. That becomes r into log to base 2 of 2, according to the third law of logarithm. All right, must be the log of positive numbers there, according to what we have there. All right, and we know that log to base 2 of 2 is 1, right? So log to base a of a is always equal to 1. So this bit here is going to be 1, and therefore we can conclude that r, all right, is log to base 2 of all positive numbers. What this is suggesting, what this suggests is that if we can only take the logarithm of positive numbers. All right, all that discussion suggests that we can only be talking about logarithms of positive numbers. We cannot talk about logarithms of negative numbers because there is no value of r here, so that 2 to the power, or a to the power of that value, is going to be a negative number. So consequently, in the reverse direction, we can only look for the logarithms of positive numbers, kind of like our discussion about the square root function. Okay, so the argument of a logarithmic function must be positive for the function to be real valued. So if this is going to be a real number, then whatever we are putting inside here, the argument, has to be a positive number. Okay, and this is the reasoning that we use to determine the domain for a logarithmic function. Let's see if we can answer some questions. So just remember that the argument always has to be positive. The expression inside the logarithmic function there has to be positive for it to have a real value. Okay, so here is an example. Find the implied domain and range of the logarithmic function f of x is log to base 5 of x. So the base doesn't really matter. The rule remains the same. So this is very quick. The argument is simply x for that logarithmic function. So we reason that the argument x has to be greater than 0. Not greater than or equal to, it cannot be 0. It has to be greater than 0. And this is the domain. We can write this in set builder notation if we must. So x is all real values that are greater than 0. And that is our domain. Okay, the logarithmic function graph is always looking like this. So the y-axis is an asymptote. okay, the graph will pass through 1, okay, because the value of x for which the value of x for which the function becomes 0, if x is 1, log of 1 to any base is always 0. So x has to be 1 here, and this is then how the graph of this particular function looks like. All right, let's look at the next. So that's example 1. We found the domain. Let's think about the range. If you look at this, the range must be anything from negative infinity to positive infinity. So we can say that the range y is real such that y lies between negative infinity. That doesn't look nice, but if you can see that, negative infinity to positive infinity, or better still, just saying y is real is enough. Negative infinity to positive infinity, y is real is sufficient. You should already notice that there is some kind of swiveling here or exchange, that for an exponential function y is 5 power x, the domain is x is real, and the range is y is greater than 0. Okay, y is always greater than 0. So any value of y greater than 0. So for the exponential function. For the logarithmic function, y is log to base 5 of x. The domain, now you can see, is x is greater than, and y is greater than 0. Greater than 0, x is greater than 0, and y is real. So it's like they have kind of exchanged, and we will see that this actually is one of the features of a function and its inverse. All right, so a function and its inverse are such that the domain of the function, it becomes the range of the inverse of the function, and the range of the function becomes the domain of the inverse of the function. So this is a property we will come to see when we look at the inverse function, the inverse of a function. Questions about determining the domain and range of logarithmic function tend to be HL as opposed to SL or AI. But you should still know why, whenever you are given a logarithmic function, it is always important to note that that argument has to be positive. You see that especially in integration. All right, let's look at the next. Find the implied domain and range of the logarithmic function log to base 2 of 3 minus x. So once again, the argument has to be greater than 0. So we reason that 3 minus x has to be greater than 0. So minus x has to be greater than minus 3 by moving 3 to the other side. If we divide both sides by negative 1, we have x. The sign of the inequality flips, is less than 3. So this function is on less than 3. So if we sketch this, we can write the domain here as x. Here are all real numbers such that x is less than 3. That is sufficient for the domain. We want to find the range. So we go to 3, point where 3 is. This is the x-axis and that's the y-axis. Now we know 3 has to be the asymptote. It's a vertical asymptote like that. And so our graph must, we can ask ourselves, where does the graph cross the x-axis, all right? And we reason that where it crosses the x-axis, this function here, let me just remove a bit of this so it is visible. Right, so that is our y, okay? So we reason that the function is going to be 0 at the x-intercept. So log to base 2 of 3 minus x must be 0 at the x-intercept. All right, if we take change to index notation, we get 3 minus x is 2 power 0, which is 1. All right, so minus x equals negative 2. So x is going to be 2. So this graph crosses the x-axis at 2. All right, so I can draw that like that. We can also find the y-intercept, of course, somewhere there. At the y-intercept, x is 0. So if we put x is 0 there, this must be the point log 2 base 2 of 3. Okay? And so this is how this graph looks like. The range, without going into too much working anymore, the range is clearly all real numbers from negative infinity to positive infinity. Okay? I hope you are understanding this. It doesn't matter how complicated a question is brought to you. If you reason using the basic axioms or the basic ideas, the basic rules, you will never get lost with this kind of questions. Right. The next one there, find the implied domain and range of the logarithmic function. Once again, we don't care about the plus 2 there, right? It might be useful for the range, but for the domain, it is still the argument of the logarithmic expression there. So once again, 2x minus 3, the argument has to be greater than 0. 2x must be greater than 3, and x has to be greater than 3 over 2, 1.5. And so the domain is x, is all real numbers, so that x is always greater than 3 over 2. That's enough to do. What about the range? Well, we know this x is greater than 1.5, so we can put 1.5 there, 3 over 2. So this has to be our asymptote, and so our graph must be going this way. It is greater than, so it has to be moving in this direction. We can find the x-intercept by, what is the x-intercept? We can find the x-intercept. I will, which space? I can use this space here. So by saying 2 plus log 2 base 3 of 2x minus 3, this has to be equal to 0 at the x-intercept. So log 2 base that is negative 2. I can use this space here. Let's see if I can use this. Yes. So log 2 base 3 of 2x minus 3 has to be equal to negative 2. That means 2x minus 3 equals to 3 power negative 2, which is 1 over 9. Check it out and see that this is fine. 2x is 3 plus 1 over 9, which is 27, and so 28 over 9, and so x has to be 14 over 9. So this point here is 14 divided by 9. If somebody wanted us to find the coordinates of the x-intercept, which you usually have to do when we are asked to sketch a curve like this, all right? We put the y-axis there, put the x-axis, and this is sufficient, and it doesn't matter. We can still see that the range will be all real numbers, all right? This is how we would need to solve this question if we were looking for the domain and range. Okay? Right. I believe I have some questions for you to try now. Let's see. Right, so here is your turn. You are given that f of x is 2 log 2 base 3 of x plus 1 minus 5. Find the domain and range of the function, expressing your answers in set builder notation. And part B there, I've made it orange intentionally because it requires you to relate to transformation. Describe fully the transformation that maps the graph of y's log 2 base 3 of x onto the graph of the function f of x. So if you've done a transformation of function, this should be easy to see. give it a try and let's see what you have. Okay? Other than that, I also want you to try other questions here. All right, find the domain of the function. So this time I'm not really worried about the range. Your job is just to find the domain of the function, and we should be fine. All right. I believe that's the end of this video. Thank you very much. I hope you enjoy it. Let me know what you think, and if you like the video, please like it. Or if this is your first video, please subscribe so that you're able to see the other videos when they come up. All right, thank you very much. We are going on to video number 11. Bye.